Jai Hind students, welcome to my YouTube channel. Students, your time is limited. Yes, your time is limited. So please don't waste it. And don't waste it living someone else's life. Don't be trapped by dogma, which is living the result of other people's thinking. Don't let the noise of others' opinion drown your own inner voice. And most important, students, have the courage to follow your heart and intuition. They somehow already know what you truly want to become. Everything else is secondary. So students, with that note, let's begin this session. And in the previous lectures, what we have discussed was magnetic elements of Earth. We have discussed magnetic declination, magnetic inclination, horizontal component of Earth's magnetic field, and then various terms and definitions. Now let's make use of those theoretical concepts in solving these selected numericals, right? Let's start with the first question then. First question is, students, the declination at a place is 12 degrees east of north. Declination, that's the angle between the geographical meridian and the magnetic meridian, right? So, let's indicate it with the help of a diagram. This is geometrical north, this is geometrical south, this is west, and this is east. Now, the declination at a place is 12 degrees west of north. 12 degrees west of north. So, this is the geographical axis, isn't it? This should be the magnetic axis. This must be the magnetic axis, which is given to be angle of 12 degrees west of north. This is given to be 12 degree. This is 12 degrees west of north. So this must be magnetic south and this must be magnetic north of Earth. So this is the mariner's compass. This is the mariner's compass needle. This must be the north pole of the magnetic compass needle. And this is the magnetic axis. Clear, students? And this angle, it is given to be 12 degrees. Again I repeat, students, magnetic declination is the angle between the geographic meridian and the magnetic meridian. So here the declination at the place is given to be 12 degrees west of north. 12 degrees west of north, right? So this is where the ship is actually heading. 12 degrees west of north, right? Now the question is, find in what direction a ship must steer so as to reach a place due east. So the ship is required to reach a place due east. So in what direction the ship must steer? So in order to reach a place due east, it should steer through an angle of, this is 90 plus 12, that is at an angle of 102 degrees in the clockwise direction. In the clockwise direction. So this is the answer, students. So the ship, in order to steer, in order to reach a place due east, must steer from its original position at an angle of 102 degrees in the clockwise direction. 102 degrees in the clockwise direction. Clear, students? So that's the answer. So for solving these questions, you need to draw these diagrams, right? So we are over with question number 1. Now let's concentrate on question number 2. Question number 2 is actually a similar question, somewhat similar. I'll read it for you. Question number 2 states that a ship is sailing due east according to mariner's compass. As per the mariner's compass, the ship is sailing due east. If the declination at that place is 18 degrees east of north, what is the true direction of the ship? So this is again a very interesting question. We need to represent it with the help of the diagram. So again, let this to the geographic axis. This will be geographical north, right? And this will be geographical north, and this will be geographical south. This is geographical west, and this is east. Now the declination of that place is 18 degree east of north. 18 degree east of north, right? 18 degree east of north. So it should be like this. This should be the magnetic axis. This is the magnetic south of Earth and this is the magnetic north of Earth. This is the magnetic axis, this is geographic axis. And the angle between the vertical imaginary planes passing through geographic axis and the magnetic axis, which are known as geographic meridian and the magnetic meridian, the angle between them, that is known as magnetic declination. Here it is given to be 18 degree east of north. 18 degree east of north, right? This is it. Now, as per the Marinus compass, the ship is moving due east. So this is as per Marinus compass. As per Marinus compass, it is moving due east. Actually, as per Marinus compass, the magnetic compass must be directed along this direction. Okay, this is the direction. It is at angle of 90 degree. This is magnetic south, magnetic north. So this angle must be also, this is 90 degree, this is also 90 degree. So this angle must be equal to this angle, which is equal to 18 degree. So actually, at that place, the magnetic declination is given to be 18 degree east of north. So what it means is that if the ship is sailing due east as per the Marinus compass, it is sailing due east, but actually it should be along this direction. Actually, the ship must be moving along this direction. So the actual direction, the true direction of the ship is 18 degree, this is south, 18 degree south of east. 18 degree south of east. This is the actual direction in which the ship is moving. This is the actual direction in which the ship is moving. Right? So again I repeat, students. This is the geographic axis, north, south, west, east, isn't it? Now magnetic declination at the place is given to be 18 degree east of north. So this is the magnetic axis. So draw a perpendicular over here. So as per the Marinus compass, it is moving due east. But actually it should be moving along this direction. Due to the magnetic declination, it should be moving along this direction. So this angle is equal to this angle. So actually the ship is moving along this direction, which is not exactly towards east, but which is 18 degree south of east. So that should be the answer, right? So we are over with question number 2 as well. Now let's proceed to the third question. Third question is pretty important one. And here the theoretical knowledge will be used. So let me read the third question for you. The true angle of depth at a place is 45 degree. If the plane of the dip circle is turned through 60 degree from the magnetic meridian, what will be the apparent? Apparent means virtual value of the angle of dip at that place, right? So angle of dip, students, first you should be aware of the angle of dip. The angle which the intensity of Earth's total magnetic field makes with the horizontal, that is known as the angle of dip, right? And whenever a bar magnet is suspended freely, it will align itself along the direction of the Earth's magnetic field and will thus lie in the magnetic meridian. Clear? So, as per this question, let us try to represent it in the form of a diagram. So, suppose, let us consider this to be a vertical plane which passes through the magnetic axis. So, this will be known as magnetic meridian, right? This is a vertical plane which we are assuming to be passing through the magnetic axis and thus would be known as magnetic meridian. As I have told you, a freely suspended magnet, it will align itself along the magnetic meridian, it will lie in the magnetic meridian and then it will dip through some angle with respect to the horizontal. and that angle which the Earth's total magnetic field makes to the horizontal, that is known as angle of dip. So the true angle of dip at a place is given to be 45 degrees. So this is the direction of the Earth's total magnetic field. This is B, and it is making an angle of 45 degrees with the horizontal. Right, students? So if you resolve this B, then this is BH. It will be equal to B cos 45 degree, and this is BV. This is the vertical component. It will be equal to B sin 45 degree. BH is the horizontal component of the Earth's magnetic field. BV is the vertical component of the Earth's magnetic field. Now students, most important part. The plane of the dip circle is turned through 60 degrees. This is the plane of the dip circle. Dip circle is a device which is used to measure angle of dip, right? And that is a simple instrument in which the magnetic needle can move freely in the vertical plane. Now earlier it is in the magnetic meridian. Now it is moved through an angle of 60 degrees, right? So it can be represented like this. This is another plane. Suppose this is another plane. Like this. And it is inclined at an angle of 60 degrees. It is rotated. So basically, the dip circle is turned through angle 60 degrees from the magnetic meridian. This is the magnetic meridian and it is turned through an angle of 60 degrees, right? What will be the apparent value of the dip? So here what we do is, this is the plane. This is the new plane where the angle of dip is to be found. Here suppose the angle of dip is del dash. Right, students? So this is BH. This is the horizontal component of Earth's magnetic field. So what will be the component of Earth's magnetic field along this plane? What is the horizontal component on this plane? This is BH. It is making an angle of 60 degrees. So the horizontal component of Earth's magnetic field in this new plane is BH cos 60 degrees. Am I clear, students? And what about its vertical component then? It will remain same. The vertical component would remain same. It won't get unchanged. So the vertical component of Earth's magnetic field at a place along different directions is same. That is, it will remain BV. Clear? This is a very, very important concept. Now, this is the magnetic meridian. Along any other plane, along any other direction, the vertical component, it will always remain constant. It is the horizontal component of the Earth's magnetic field that will be different in different planes. So this is one of the important points. And second is the horizontal component, that is BH, will be different in different planes. So therefore, in the magnetic meridian, the horizontal component of Earth's magnetic field is BH. If the plane is rotated through an angle of 60 degrees, then on that plane, the horizontal component would be BH cos 60 degrees. Clear, students? Okay. Now, these are the two main important points so as to enable us to solve this question. Now, a simple thing. Del is the true angle of dip. Del is the true angle of dip. Therefore, we are aware tan del is equal to BV divided by BH. This we are already aware of, isn't it? Put this as equation 1. Now, in the plane 1, This is suppose plane 1. This is the plane which is the magnetic meridian. Here, the true value of angle of dip is tan del equals to dV by dH. That we are already aware. In plane 1, the apparent angle of dip would be tan del 1. It would be equal to dV. Vertical component in the different planes would also remain same. It won't change. And the horizontal component is BH dash, which is BH cos theta. Clear? So BV over BH, it is tan del. Del is the true angle of dip. So tan del 1, it will be equal to tan del divided by cos theta. So students, from MCQ point of view, you need to remember this particular formula, right? BV divided by BH, that's the true value of angle of dip, tangent of the true value of angle of dip. So again I repeat students, the angle of dip is the angle which the Earth's total magnetic field makes with the horizontal, isn't it? Now, in case the plane is rotated or it is displaced through an angle of, or turned through an angle of 60 degree, here the quotient is given to be 60 degree, then in that plane the vertical component will remain same, but the horizontal component in the different planes would be different. In case the horizontal component in the magnetic meridian is BH, then if the plane is rotated through angle 60 degree, then in that new plane the horizontal component would be BH cos 60 degree. Clear? So here theta is the angle through which the plane is rotated. The magnetic meridian, the plane is rotated with respect to the magnetic meridian, right? Del is the true value of angle of dip and del 1 is the apparent value of the angle of dip, right? So now let's substitute the value and get to the answer. Let us get the answer. So tan del 1, it would be equal to tan, true value of angle of dip is 45 degree, divided by cos, the angle through which the plane is rotated, that is 60 degree. Tan 45 degree is 1, cos 60 is half, so it will be equal to 2. Therefore, the apparent angle of dip is tan inverse 2. So this is the answer, students. The apparent or the virtual value of the angle of dip when the plane is rotated through an angle of 60 degree would be tan inverse 2, right? So this was a very important question. Okay, now let's consider question number 4, which is very, very important one. Concept is based on question 3 only, right? If del 1 and del 2 be the angles of dip observed in two planes which are at right angles to each other, and del is the true angle of dip, then we are supposed to prove that cot squared del 1 plus cot squared del 2 is equal to cot squared del. Two planes are given to be at right angle to each other. Suppose students, this is plane 1, this is plane 1, and this is plane 2. These two planes are at right angle to each other. The angle between these two is 90 degree, right? These are the two planes which are at right angle to each other, these two. Clear, students? I am talking about these two planes, this one and this one. These are the two planes which are at right angle to each other, right? Okay, this is first and this is second. This is plane 1 and this one is plane 2. Now students, the angle between these two is 90 degree. Now, the true angle of dip is del. The true angle of dip, del, would be in the magnetic meridian, isn't it? The Earth's total magnetic field, it will lie in the magnetic meridian. Therefore, the Earth's total magnetic field, the angle which it makes to the horizontal, that is the angle of dip. So, this is suppose, let us consider this to be the magnetic meridian. This is the actual magnetic meridian. That is, this is the vertical plane which passes through the magnetic axis, and therefore the Earth's total magnetic field will be in this plane. BH will also be in this plane, right? So let us consider BH is along this direction. This is BH. This is the horizontal component of Earth's magnetic field. Obviously, it will be in the magnetic meridian. Now, if we consider this to be making an angle theta with plane 1, then in plane 1, the horizontal component would be, in plane 1, the horizontal component would be BH cos theta, isn't it? While in plane 2, what will be the horizontal component in plane 2? The angle between these two is 90 degree. So in plane 1, if it is BH cos theta, in plane 2, the horizontal component is BH sin theta. While as discussed in the previous question, I have stated the vertical component will remain same. This is the vertical component. This will remain same for all the three planes. This is BB, vertical component. So students, the most important point to be noted down is that the horizontal component of Earth's magnetic field BH, it obviously will lie in the magnetic meridian. But when the plane is rotated through some angle, then the value of BH at different planes would be different. But the vertical component will remain constant. Vertical component will remain same, that is B. Now, if you take a top view, then the diagram will be somewhat like this. This is plane 1. This is plane 2. The angle between them is 90 degree, right? And this is the magnetic meridian. This is the magnetic meridian. So BH would be along this direction. So if the magnetic meridian is assumed to make an angle of theta with plane 1, then the horizontal component of Earth's magnetic field in plane 1 would be BH cos theta, while the horizontal component of Earth's magnetic field in plane 2 would be BH sin theta. Now I think it must be pretty clear. This is the top view. Clear, students? Okay, now del is the true angle of dip. True angle of dip. Therefore, we are aware, students, tan del, it will be equal to BV divided by BH. No doubt regarding this. Clear, students? Now, for plane 1, the angle of dip is given to be del 1, tan del 1. It will be equal to, vertical component will remain same and horizontal component would be BH1, which is BH1, it is BH cos theta. BH cos theta. Now BV by BH, that is tan del. So tan del divided by cos theta. This is the formula which we have proved in the previous numerical as well. So students, from here, what do we get? Cos theta, it would be equal to tan del divided by tan del 1. Put this as equation number 2. Right? Similarly, we'll follow the exact steps for plane 2. The angle of dip is del 2. Tan del 2, it would be equal to BV divided by the horizontal component along plane 2, that is BH2, which is BV divided by BH2 is BH sin theta. BH sin theta. Now BV divided by BH is tan del. Del is the true value of angle of dip. So tan del divided by sin theta. Right? Which implies that sin theta, it is equal to tan del divided by tan del 2. Put this as equation number 3. So students, we are supposed to prove this expression, cot square del 1 plus cot square del 2 is equal to cot square del. So now what we are supposed to do is simply squaring and adding second and third. I think we should get the result. Squaring and adding second and third. Here it's cos theta, here it's sin theta. So left hand side would be cos square theta plus sin square theta. That would be equal to 1, isn't it? It will get eliminated. So what we do is second square plus third square. Second square, it is cos square theta. It is equal to, okay, first left hand side plus sin square theta. It will be equal to tan square del divided by tan square del 1. Tan square del 1. Right? Now similarly, on squaring this, what we get is plus tan square del divided by tan square del 2. Obviously, cos square theta plus sin square theta is 1. So here, tan square del can be taken as common. 1 divided by tan square del 1 plus 1 divided by tan square del 2. So, let's rearrange the terms and this will give you the answer. Reciprocal of tan theta is cot theta. So 1 by tan square del would give us cot square del. It will be equal to cot square del 1 plus cot square del 2. So we have proved this particular expression. So these two questions are very, very important. Okay students, question number 5 then. The horizontal component of Earth's magnetic field at a place is given to be 0.2 G. G stands for Gauss. It's a unit which is used to measure Earth's magnetic field, right? So, BH is given to be 0.2 Gauss. Here, I must state that 1 Gauss is equal to 10 raised to power minus 4 Tesla. Tesla is the SI unit of magnetic field. So that's the relationship between Gauss and Tesla. 1 Gauss is 10 raised to power minus 4 Tesla. Gauss is basically the unit of magnetic field which we use to describe the Earth's intensity, Earth's total intensity of Earth's magnetic field, right? So anyway, another information is total magnetic field is given to be 0.4. It is also given in the same unit. It is given to be 0.4 Gauss. We are supposed to find out the angle of dip, right? So what's the relationship between these two? BH is equal to B cos del, isn't it? We are aware of it. Del is the angle of dip. Remember this diagram. If this is the magnetic meridian, means it is an imaginary vertical plane which passes through the magnetic axis. And suppose this is the direction of Earth's total magnetic field. So it will align itself and then the magnetic, freely suspended magnet will tend to dip. And the angle through which it dips with respect to the horizontal, that is angle of dip. And if you resolve this, this will be BH. It is equal to B cos del. That is what I have written over here. Now let's substitute the value. BH is 0.2 Gauss. No need to change the units because both are of the same units. So it is 0.4 cos del. So therefore, cos del, it will be equal to 0.2 divided by 0.4. It is equal to half, which implies that cos del is equal to cos 60 degree, which implies that angle of dip must be 60 degree. So this is the answer, students. So the angle of dip at the place is 60 degree. Let's move on to the last question. What is the angle of dip? Again, we are supposed to find out the angle of dip at a place where the horizontal and the vertical component of Earth's magnetic field are given to be equal. That is, it is a place where BH is given to be BV. It is constant. We are supposed to find out the angle of dip at that place, right? So obviously, tan del, it is BV divided by BH. Since both are same, therefore the ratio would be 1, which implies that tan del is equal to tan 45 degree. Tan 45 degree is 1, which further implies that del is equal to 45 degree. So students, do remember it, that at a place where the angle of dip is 45 degree, it clearly suggests that at that place the Earth's horizontal component of magnetic field is exactly equal to its vertical component, right? So we have done question number 6 as well. So students, I hope you have got benefited by doing these questions, right? These are the questions which needs to be attempted only when your theoretical portions are clear. And in the description section of this lecture, I will be giving you the link of the previous 2 lectures. In case you find any difficulty in understanding the concepts, you can fall back on those lectures, right? So that's it for this particular session, students. Do join me in my next lecture, right? Thank you.